All right, moving on. Let's take a look at number 22. We're solving a cubic inequality. Now, solving a cubic inequality, our first step is we got to find our critical values. All right, find the critical values. And the critical values are your zeros of the related equation. Right, so zeros of your related equation. So for right now, let's find that. So let's go ahead and solve the related equation to find those. So we'll find the solutions to the equation that relates to this cubic inequality. So that implies when does 2x cubed minus 5x squared equal 12x. So forget about less than or equal to for right now. Now to solve that, right, we're going to go ahead and set it equal to 0 and try to factor. We'll try to solve by factoring. All right, so again, trying to set equal to 0. As we do that, we get 2x cubed minus 5x squared minus 12x equal to 0. And now we can factor, right? So our GCF, right, we'll notice that each of these terms has at least a x in it. So we'll go ahead and factor that out. GCF is x. So as we factor an x out, we're left with 2x squared minus 5x minus 12 equals 0. And with that, we have a factorization. We have a linear factor, and then we have a quadratic trinomial. Let's go ahead and factor that quadratic trinomial. We need a 2x and an x up front for the 2x squared. What factors of 12 do you want to use? Let's try 3 and 4. We put a 4 on the outside and we put a 3 on the inside. Well, with a minus 4, we would have an outside product of negative 8x, right? And we would have a inside product of 3x. So again, just checking our factoring, that adds up to negative 5x. So again, you're checking that. It does check out. We get, of course, negative 12, and you multiply the 3 and negative 4 together. So we've done our factoring. So now we use our zero factor property, and x can equal 0, or 2x plus 3 can equal 0, or x minus 4 can equal 0. So as far as our zeros go, we got 3 zeros for this equation. And this was a degree 3 cubic polynomial, which means we can have up to 3 zeros. And we do. We have 3 different zeros in this cubic degree 3. So x equals 0, x equal to negative 3 halves, or x equal to 4. So there are critical values. So finding the critical values, we've got those. Let's go ahead and write those up here. So again, we got negative 3 halves, the smallest critical value, 0 and 4. So what we're going to do is set up now what we call our test intervals. So that's our next step. All right, what are the test intervals? What are our possibilities for solution set intervals? So I'll place these on here. Negative 3 halves, 0, 4. So if I place those on there, my critical values. Now we had a less than equal to problem. So once we had equality, we're going to include these as in our solution set, because we know this when it equals 0. So one of our possibilities is negative infinity to negative 3 halves with a bracket. All right, we have these numbers in here to test. And of course we have the numbers between there, which is negative 3 halves to 0. Right, we also have the numbers between 0 and 4, 0 to 4. And then our fourth and final possibility is 4 to infinity. So here's our x line, all real numbers x. That's where our solution set intervals they're coming from, are those possibilities. So our last step, so now we're going to test it. So pick a test value, some easy plug in. So negative 3 halves, negative 1/2. Let's pick negative 2. That'd be an easy one to plug in. So I'm going to use negative 2 as my test value for that interval. what's the number easy to work with between negative 3 halves and 0? I'm going to use negative 1. And 0 to 4, I'm going to use 1. 4 to infinity, I'm going to use 5. So any number, we only need 1 to test it. So let's see if this is a solution. So we test, let's plug it back in. So 2 times x cubed, 2 times negative 2 cubed, minus 5 times negative 2 squared must be less than or equal to 12 times negative 2. So as we simplify that down, that's 2 times negative 8 minus 5 times 4, right, less than or equal to negative 24, which is negative 16 minus 20, less than or equal to negative 24, which is negative 36, and negative 36 less than or equal to 24, what do we get? We get a true statement. It is less than negative 24. So it checks. So since it checks, right, it's in the solution set. So all of these numbers we picked with negative 2 works. Now as we go to our next interval, negative 3 halves is 0. We're going to test with negative 1. So let's plug it in. So 2 times negative 1 cubed minus 5 times negative 1 squared, is that less than or equal to 12 times negative 1? Well, as we simplify down, that's 2 times negative 1 minus 5 times 1, less than or equal to negative 12. And that gives me a what? Negative 2 minus 5. Negative 2 minus 5, negative 7. Negative 7 is greater than 12. That didn't check. So that means we got to throw out that interval. Now we got 2 more intervals to test. So what happens? Let's test this interval. How about 0 to 4? I need to test it. Now again, we're picking 1. So that'd be 2 times 1 cubed, right? Minus, what? 5 times 1 squared, less than or equal to 12 times 1. So that simplifies to 2 times 1 minus 5 times 1 less than or equal to 12, which is 2 minus 5. 2 minus 5, negative 3. And yeah, negative 3 is less than 12. It checks. So we got another solution set interval, right? The values there from between 0 and 4. And our last possibility to test, right? We need to test the last interval, 4 to infinity. And we picked 5 as our test value. So let's go ahead and test that. So 2 times 5 cubed minus 5 times 5 squared, less than or equal to 12 times 5. Well, 5 cubed, that's 5 times 5 is 25, times 125. So we got 125 there, minus 5 times 25 here, less than or equal to 60. Well, that's 150 minus 125, less than or equal to 60. So I have 25 less than or equal to 60. As I simplify that down, now be careful, check your arithmetic. All right, what do we get there on that one? So we plugged in that value. All right, make sure we're checking that correctly. All right. Oh, and somebody check my work. What's 2 times 125? I already double checked my arithmetic. Doesn't give you 125. That gives you what? 250. 250 minus 125, of course, is 125. So 125 is not less than 60, greater than 60. So it doesn't check, so we throw it out. So in the end, we have 2 intervals that make up this solution set. So our solution set are all real numbers less than or equal to negative 3 halves, right? Or all the numbers greater than or equal to 0 and less than or equal to 4. Right? And again, that's answer choice what? C? C is our answers. That's solving a cubic inequality. And you can also graph it to see that too. If you graph it, you'll see a graph take place below the x-axis between those values of x, between negative infinity and negative 3 halves, and between 0 and 4. So it'll be an easy way to check it also on your grapher. So it's nice to look at them graphically too. when you're doing these. So again, pull out your calculator if you need to, right, to get a graph of those. Right? So again, you can take the time to do that. All right, let's go to problem number 23. Now, number 23, we've got a inverse function problem. To determine whether the given function is 1 to 1, 1:1, and find, if so, find the formula for the inverse. Find the inverse function. So find f inverse of x if it exists. So we're proving 1 to 1. That will be our first step. All right, is f of x 1 to 1? So what I'm going to do is quickly check with the horizontal line test. So if we go back to reviewing 1 to 1, 1 to 1 function is any function which each y value is exactly 1x. To be a function, each x must give you 1 y, so each member domain corresponds to exactly one member of the range. 1 to 1, the converse, the inverse of that's true. Each member in the range must give you exactly one member of the domain. So to do that, use your horizontal line test. So let's go ahead and graph in this function. So let's pull up our calculator. All right, let's go out here and clear out our last one. Let's get a picture of this one. Now, cube root, shortcut for that, math command, command 4 is your cube root symbol. So hit math and 4, and then you type in x minus 5. And as you graph that, right, this cube root function, now that does not give me a good picture to graph. So yours probably will. I'm going to go in here, I'm going to put this in on my Desmos calculator, give you a better picture. Now I'm going to put it in over here, so I don't have the shortcut here on this screen for cube root. I'm going to put in this function using, again, remember, cube root is the power of 1/3. So I'm going to put it in here with a rational exponent. So that would be an exponent of 1 divided by 3. Now here's a better picture. Here's your picture you got on your TI. You see this graph, and it definitely passes the horizontal line test. This is a graph that's always rising, increasing from left to right. Any function that's always increasing or decreasing. It's a characteristic of a 1 to 1 function. Nowhere on that graph, right, would you find a y value of more than 1x, right? Because most of the horizontal line will cross that graph as 1 point. Right, in a horizontal line, y is constant. The only thing changes is x, so you wouldn't want it to cross more than once. If so, you'd have more than 1x for the same y. So with that said, definitely a 1 to 1 function. So going back to our definition, yes. Right, and we prove that by the horizontal line test, HLT. So what does that imply? So that implies f inverse of x exists. So that produces the existence of the inverse function. So let's move on and let's find it. So now let's go find f inverse of x, which again notated by superscript -1. Now break that down, basically 4 steps. All right, our first step, let's go ahead and look at the function in terms of x and y. So get rid of function notation. Look at the equation of the two relating variables. So I'm going to rewrite f of x of y. All right, and then we're going to start to look at the inverse. So step 2 is to find the inverse relation. So we're going to interchange, right, x and y. Those are the two relating variables. So y becomes x, and x becomes y. So swapping out x and y. And then our third step is we're going to solve for y. So now we got to go get y out of that cube root. So to do that, right, we're going to take this equation. So right now we got a cube root. If we want to solve for y, we need to, what? Cube both sides of the equation to get rid of a cube root. So right now, again, our equation is x equal to the cube root of y minus 5. And again, to eliminate the cube root, we would raise it to the power of 3. So using the principal powers, whatever the index of your root is, that's the power we need to raise it to. Square root, we'd square it. So it's a cube root, we cube it. So x cubed equals y minus 5. Well, one more step, right? We'll solve for y. So we need to move that minus 5 over. So we'll go ahead and add 5 to the other side of the equation. So that implies x cubed plus 5 equal y. So that implies our inverse function. F inverse of x equals x cubed plus 5. So there's the inverse function. This cube root had a cubic polynomial. Answer being A, right on that one. And again, if you go back to your grapher, let's go back to our calculator. Let's put in what we just found. Let's put in x cubed. All right, I want to show you these two graphs together, x cubed plus 5. All right, one thing about inverse functions, they're always symmetrical to the line y equal x. All right, this line passing through the origin of slope of 1. And you can see their intersections all occur right here at that line. So you can see that symmetry with these two graphs about that line. So that's a quick way to check, right, inverses, is to graph them. Look at them graphically. All right. So moving on, let's go to example here of solving a exponential equation. In solving an exponential equation, all right, the first step, now notice what's an exponential? This is a natural exponential equation. We have our natural base e, right? E is our number 2.713 approximately. But up here in our exponent contains our variable. So we got to solve for x. We want to know what x equals. Our first step is to isolate the exponential term. So we're going to solve this algebraically. We're going to work on getting x, right, out of the exponent. We've got to isolate the exponential term. So let's go ahead and do that. So with 25 minus e to the negative 0.32x equal to 10, right, we got a couple steps to do. So let's go ahead and subtract the 25 over. So as we do that, right, we would have what? Negative e to negative 0.32x equal to negative 15. And then we'll go ahead and get rid of the negative. Let's go ahead and divide out negative on both sides. And as we do that, we get our term isolated, e to the negative 0.32x equals 15. So we isolate that term. Now, here's where our work comes in. How do we get x out of the exponent? Well, we like to be able to write both sides of the same base, and we could drop down the exponents. But since we can't, so we're doing a natural number e, we're going to introduce logarithms. So we're going to take the log of both sides. So we're going to introduce, all right, logarithms, log properties. So since we're dealing with log or natural number, let's do log base e. So I'm going to take the natural log base e, abbreviated ln, do natural log of both sides. So simplify easily. So you can do any log base you want, but I'm going to use log base e. So natural log. As I do that, review one of our properties from earlier this semester. So we remember our same base rule. So if you remember this property, what's log base a of a dx simplified to? X. So you can use that here. So all of this, right, is equal to negative 0.32x. So using our properties, this is negative 0.32x equal to the natural log of 15, and we can divide out our coefficient and have our solution. So as we divide out on both sides, negative 0.32, we get our answer. Here's our solution for x. So what does x equal? The natural log of 15 divided by negative 0.32. Now that's the exact. And we can also give them a decimal. So if you want, one thing I did, I used the log base e, right? Because on my calculator, we have the log base e key and log base 10 key on the side. So we can easily type that in. So what is a natural log of 15, right, divided by negative 0.32? Right, I get negative 0.8462 There's my x value, right? There's my answer for this one. So we want to round it to a decimal. And again, if you're not sure of your answer, you can always check it graphically, right? You can graph it and look for intersection point. But again, there it is. There's ln of 15, right, divided by negative 0.32 in this problem. So let's go back into our problem here. We'll write in our approximation. So negative 8.463 if we're rounded to the nearest thousandth. There's our approximation. But that's our exact. And again, I mentioned to you earlier, you can graph these and show that intersection too if you like. But that's solving exponentials. So we'll take a break and we'll continue on and finish up the review.